Hello there, and welcome. Tonight we're going to dive into one of the most fascinating stories that science has uncovered in recent years, and it's happening right in our own cosmic backyard. For a long time, we looked up at the night sky and saw the Milky Way as this beautiful, relatively stable spiral of stars. But here's the thing, that peaceful picture we had? It was incomplete, very incomplete. Over the last few years, scientists have been working like cosmic detectives, piecing together clues hidden in the light and motion of billions of stars. And what they've discovered is that our galaxy has lived quite the turbulent life. The Milky Way isn't the calm, orderly place we once thought it was. Instead, it's more like an ancient cosmic city that's been through multiple invasions, mergers, and transformations. So tonight, we're going to unpack what we've just learned about our galaxy's hidden past. We'll talk about the violent collisions that shaped us, the mysterious waves rippling through our stars, the strange glowing heart of our galaxy, and even some unexpected visitors that are still being absorbed into our galactic home. By the end of this, you'll understand that the Milky Way's story is far more dramatic and fascinating than we ever realized. Let me start with this striking fact. The Milky Way wasn't always one galaxy. It was built from multiple galaxies merging together over billions of years. Think of it like construction. If you wanted to build the largest city possible, you might start with several towns and eventually combine them into one metropolis. That's essentially what happened to our galaxy, except on a scale so enormous that it's difficult to even comprehend. For the longest time, astronomers knew this must be true in theory. Computer models and observations of distant galaxies showed that large galaxies grow by absorbing smaller ones. But the challenge was proving it with our own galaxy. How do you figure out what happened billions of years ago when all the evidence is scattered around you right now? Well, scientists found a way. Imagine if you could trace your family's DNA back thousands of years. You'd see patterns of where your ancestors came from, when they migrated, and where they mixed with other families. That's essentially what astronomers do with stars. By studying the positions, movements, and chemical compositions of billions of stars, researchers have been able to reconstruct our galaxy's merger history. The key tool here has been the Gaia Space Telescope, launched by the European Space Agency. Gaia is like the world's most precise surveying instrument, but for space. It measures the positions and movements of stars across our galaxy with extraordinary accuracy. But Gaia alone wasn't enough. Researchers combined Gaia's data with computer simulations and artificial intelligence to figure out which stars belong to which family of stars that came from the same progenitor galaxy. So what did they find? Scientists discovered that at least 5 major galaxies merged with what eventually became the Milky Way. These ancient galaxies had wonderful names given by astronomers: Sagittarius, Sequoia, Kraken, the Helmy Stream, and Gaia Enceladus. Each of these contained between 100 million and billions of stars. But here's where it gets really interesting. The biggest merger didn't happen just once. Our galaxy has been through multiple massive collisions, with the largest ones occurring between 6 and 11 billion years ago. That's roughly 2 to 5 billion years after the Big Bang. The universe was young, galaxies were actively forming, and our little corner of space was about to go through a dramatic transformation. The most famous of these ancient collisions involved a dwarf galaxy called Gaia Enceladus. Picture this. Roughly 10 to 11.5 billion years ago, the early Milky Way was spinning along, minding its own business. It had already formed a decent number of stars, maybe a few billion. Then out of nowhere, Gaia Enceladus came barreling in. Now Gaia Enceladus wasn't tiny. It was a substantial dwarf galaxy, probably containing billions of stars. But compared to the early Milky Way, which was about 4 times more massive, it was like a small moon colliding with a planet. The result? Absolute chaos, but beautiful, productive chaos. When Gaia Enceladus slammed into the Milky Way, the gravitational forces were so immense that the stars from both galaxies got thrown into wild, swirling orbits. The collision also triggered something remarkable, a massive burst of star formation. Gas clouds from both galaxies were compressed together, and this compression caused the formation of billions of new stars. The star formation rate in the Milky Way reached a record high during this period. Far more stars were being born per year than in our galaxy today. You might be wondering, how do we know all this happened? Well, scientists looked at the motions and compositions of modern stars. Some of these stars still show the telltale signs of being part of Gaia Enceladus. They move in unusual patterns compared to most stars in the Milky Way, and they contain different chemical compositions. It's like finding people with a distinct accent or cultural heritage in a modern city. They reveal something about the city's history. This massive collision had another important consequence. It created something called the galactic halo. The halo is essentially a spherical region of stars that surrounds the main disk of the Milky Way. Many of the stars in our galactic halo today are the descendants of this violent merger. They're the cosmic refugees, in a sense, from that ancient collision. After the merger with Gaia Enceladus, the Milky Way kept growing. For the next few billion years, fresh gas continued to rain down on our galaxy, fueling more star formation. By about 8 billion years ago, something interesting happened. The gas began to settle into a much thinner, flatter disk, the disk we see today. This transition from thick to thin disk is crucial to understanding why our galaxy looks the way it does now. Think about it this way. In the early chaotic days of the Milky Way, after multiple mergers, everything was thick and puffy. Lots of stars moving in random directions. But gradually, the orbital motions began to favour one particular direction, the galactic plane, and over time, the galaxy flattened out. It's like if you spun a plate of spaghetti so hard that it flew everywhere. Then gradually, the gravity and rotation worked together to flatten it back into a thinner shape. More mergers to discover. Here's the fascinating part. Astronomers believe they've only identified the major mergers so far. There were likely many more smaller mergers that happened, and scientists are still finding evidence of them. For instance, in 2024, researchers discovered 2 previously unknown stellar structures within the Milky Way called Shiva and Shakti. These massive aggregations of stars, each containing over 10 billion solar masses, may be remnants of even older proto-galaxies that merged with the Milky Way more than 12 billion years ago, even before the famous collision with Gaia Enceladus. So what we're realizing is that the Milky Way's family tree is even more complex than we thought. It's not a simple story of 1 or 2 mergers. It's more like a chaotic family history with multiple generations of cosmic unions. Part 2. The mysterious wave. A cosmic ripple. We just started to understand. Now here's where things get even more intriguing. If the Milky Way had a chaotic past, you might think it would have settled into a calm, stable present. But that's not what we're seeing. In fact, just a few months ago, scientists discovered something extraordinary. Our galaxy is literally rippling like a wave in water. The discovery. A galactic undulation. Imagine throwing a stone into a calm lake. The waves ripple outward, creating patterns across the water's surface. Now imagine that happening on a galactic scale. This is what the Gaia Space Telescope revealed in 2025. The Milky Way's disk is sending out enormous waves that travel outward from the galactic centre. These aren't small, subtle movements. We're talking about waves that span tens of thousands of light years. For perspective, a light year is the distance light travels in 1 year, about 5.9 trillion miles. So these waves are incomprehensibly vast by human standards. When astronomers studied the positions of bright young stars and certain types of variable stars called Cepheids, they noticed something peculiar. These stars weren't just moving in a simple circular orbit around the galactic center. They were oscillating up and down relative to the galactic plane. It was as if the entire disk of the galaxy was warping and flexing in a coordinated pattern. To visualize this better, imagine looking at our galaxy from the side. You'd normally see a relatively flat, thin disk of stars. But now, with these new observations, scientists can see that parts of the disk are bent upward, while other parts are bent downward. And this warping is happening in a wave-like pattern. Red areas indicate stars above the warped plane, while blue areas show stars below it. The pattern repeats as you move outward from the galactic center. What could cause a wave this large? Now comes the big question. What causes a wave of this magnitude? Scientists have a few theories. The most popular explanation involves what happened long ago in our galaxy's history. When the Milky Way went through those violent mergers we talked about earlier, the gravitational impacts may have triggered oscillations in the galactic disk. Think of it like hitting a drum and watching the surface vibrate for years afterward. Another possibility is that the Milky Way's central bar, the galactic bar, is a dense, elongated structure of stars at the center of the galaxy, might be interacting with the disk in a way that creates these waves. The bar is like a cosmic stirring spoon, and as it rotates, it can create ripples in the surrounding disk. But here's the really interesting part. Scientists currently think that even the gas in our galaxy is participating in these waves. It's not just the stars oscillating up and down. The entire galactic structure is undulating in a coordinated way. When you've got that much material, billions of stars and vast quantities of gas, all moving in a synchronized wave pattern, it's actually quite remarkable. A puzzle we're still solving. What's even more fascinating is that astronomers aren't entirely sure how long these waves have been happening or exactly what triggered them. They're planning to use newer data from the Gaia telescope to investigate further. As more observations come in, we should get a clearer picture of this cosmic oscillation. But why should we care about a galaxy-scale ripple? Well, it tells us that our galaxy is far more dynamic than we realized. The Milky Way isn't just an old static collection of stars. It's actively evolving. These waves reshape how stars orbit, influence where stars form, and might even affect the long-term stability of our galactic home. Understanding them helps us understand the fundamental physics of how galaxies work. Part 3. The glowing heart, dark matter, gamma rays, and an unsolved mystery. Let's move our attention to the very center of our galaxy. If you could fly to the heart of the Milky Way, you'd encounter something both fascinating and terrifying. A supermassive black hole. This isn't a small black hole either. Our galactic center hosts a black hole with a mass of about 4 million times that of the Sun. Scientists call it Sagittarius A, and it's been the subject of intense research. But here's the puzzling part. The region around Sagittarius A is glowing with a strange, intense radiation that scientists can't fully explain. It's a mystery that's been puzzling astronomers for over a decade. The galactic center excess, a riddle wrapped in radiation. For more than 10 years, astronomers using NASA's Fermi Gamma Ray Space Telescope have observed something unexpected coming from the Milky Way's core. There's an excess of gamma rays, high-energy radiation, being emitted from the region around Sagittarius A. This gamma ray glow shouldn't be there, or at least it shouldn't be as bright as it appears to be. Think of it this way. If you were in a dark theatre and you expected to see a certain amount of light on stage, but instead you saw much more light than expected, you'd be confused, right? That's essentially what's happening. The amount of gamma radiation coming from the galactic center is significantly higher than theoretical models predicted. For years, scientists proposed different explanations. The most popular theory involved dark matter. Dark matter is one of the universe's great mysteries. We know it exists because we can see its gravitational effects, but we can't see it directly. It doesn't emit light, and most conventional telescopes can't detect it. Dark matter makes up about 27% of all matter in the universe, yet we still don't know what it is. Some scientists propose that dark matter particles in the galactic center might be colliding with each other and annihilating in spectacular explosions. These collisions could produce gamma rays. It sounded plausible, but when scientists modelled what they'd expect to see from such collisions, the pattern didn't quite match what the Fermi telescope was observing. The alternative explanation, ancient pulsars astronomers, then turned to another explanation, ancient, rapidly spinning neutron stars called millisecond pulsars. A pulsar is the incredibly dense remains of a massive star that exploded as a supernova. Some pulsars rotate hundreds of times per second, shooting out beams of radiation like cosmic lighthouses. These millisecond pulsars could potentially produce the gamma-ray glow observed at the galactic center. This explanation gained favor for a while because the pattern of radiation seemed to match what you'd expect from pulsars. But it also had problems. There weren't quite as many pulsars detected in that region as there would need to be to explain all the gamma rays. The plot twist, dark matter makes a comeback. Now here's where the story gets interesting again. In 2025, researchers using advanced computer simulations decided to revisit the dark matter hypothesis, but with a new twist. They realized that previous simulations hadn't fully accounted for a crucial factor: the Milky Way's violent merger history. Remember those collisions we talked about earlier? When smaller galaxies merged with the early Milky Way, the gravitational impacts would have scrambled the distribution of dark matter in the galactic center. Instead of being evenly distributed, dark matter might have been concentrated into unusual, lumpy structures. When scientists ran new simulations that included the effects of these ancient mergers, something remarkable happened. The predicted pattern of gamma rays from dark matter collisions suddenly matched what the Fermi telescope was actually observing. It was like finally having the last puzzle piece fit into place. What this means is that dark matter might indeed be responsible for the mysterious gamma-ray glow at the centre of our galaxy. But the reason the earlier theories didn't work was because they didn't account for how the galaxy's chaotic past had reshaped dark matter's distribution. The mergers didn't just create stars and scramble the positions of ordinary matter. They fundamentally altered how dark matter was organised. Why this matters? This discovery is significant for several reasons. First, it reinforces that the Milky Way's history of collisions and mergers has shaped not just the visible galaxy, but also the distribution of dark matter. Second, it shows that dark matter is far more complex than we initially thought. It's not evenly distributed throughout the galaxy. Instead, its density and organisation can be significantly affected by cosmic events. Third, this research is helping us narrow down what dark matter actually is. Different types of hypothetical dark matter particles would produce different signatures. By studying the specific pattern of gamma rays and comparing it to theoretical predictions, scientists are getting closer to understanding the nature of this mysterious substance that makes up most of the matter in the universe. But scientists currently emphasize that this is not a definitive answer. It's a promising hypothesis that fits the data well, but more observations and research will be needed to confirm it. Science is a process of gradual discovery, not sudden certainty. Part 4. The Satellite Mystery. Too many dwarf galaxies or just better detection? Let's zoom out from the galactic center and look at the bigger picture. Our Milky Way doesn't exist alone in space. Around it orbit numerous smaller galaxies called satellite galaxies or dwarf galaxies. These are sort of like cosmic moons, bound to the Milky Way by gravity. The most famous of these is the Large Magellanic Cloud, visible to the naked eye from Earth's southern hemisphere. For a long time, astronomers had a rough idea of how many satellite galaxies orbited the Milky Way. But recently, discoveries have thrown that estimate into question and revealed another cosmic mystery: the missing satellites problem. Let me explain this the way physicists like to phrase it. There's something called the missing satellites problem. Based on computer models of how galaxies form and how dark matter is distributed in the universe, theoretical predictions suggested that the Milky Way should have around 220 satellite galaxies orbiting it. But when astronomers looked through telescopes, they could only find about 60 known satellites, far fewer than predicted. This discrepancy bothered astronomers. Where were all the missing satellites? Were the theoretical models wrong? Were the dwarf galaxies hidden behind larger structures? Were they too faint and diffuse to detect with current technology? Scientists weren't sure. New discoveries change everything. Then in 2024, researchers using Japan's Subaru telescope discovered something surprising. They found two new potential satellite galaxies called Sextans 2 and Virgo 3. Now, finding a couple of new dwarf galaxies wouldn't normally be headline news in itself, but here's where it got interesting. These new discoveries were located in the same general region of space already under study. When astronomers calculated the density of satellite galaxies in this region and extrapolated it across the entire sphere surrounding the Milky Way, they reached an astonishing conclusion. If this region is typical of the satellite galaxy distribution everywhere, there could be at least 500 satellite galaxies orbiting the Milky Way, more than double the previous estimates, and significantly more than the theoretical predictions. This doesn't solve the missing satellites problem. Instead, it makes the problem more acute. Now we have even more satellite galaxies than we expected from theory. It's like looking for a lost book in your library, only to discover that not only is the lost book there, but there are twice as many other books as you thought you had. What this reveals about our galaxy. So what does this tell us? Well, one possibility is that our theoretical models of galaxy formation aren't quite right. Maybe galaxies can accumulate even more satellite galaxies than we thought. Another possibility is that the Milky Way is especially good at capturing and retaining smaller galaxies due to its particular size, shape, and position in space. But here's something even more interesting. The satellite galaxies that astronomers are discovering aren't like the ones observed in other galaxies. In many Milky Way-like galaxies studied in the Saga survey, a comprehensive study of 101 galaxies similar to the Milky Way, most satellite galaxies have stopped forming new stars. They're old, peaceful collections of ancient stars. But in the Milky Way itself, most of the satellites have indeed stopped forming stars, with notable exceptions. The two largest satellites, the Large and Small Magellanic Clouds, are still actively creating new stars. This is an unusual combination. It suggests that our galaxy has had a unique history of interactions with its satellite galaxies. Environmental effects on dwarf galaxies. Research from the Saga survey has revealed something important. Satellite galaxies located closer to their host galaxy, the big galaxy they orbit, are more likely to have their star formation quenched or stopped. This suggests that environmental factors play a crucial role in the life cycle of small galaxies. What could cause this? When a dwarf galaxy gets too close to a massive galaxy, like the Milky Way, the gravitational tidal forces can actually strip away the dwarf galaxy's gas. Without gas, you can't form new stars. So over time, the dwarf galaxy becomes a collection of ancient stars that will slowly fade away over billions of years. This process is happening to one of the Milky Way's current satellite galaxies, the Canis Major dwarf galaxy. It's currently being torn apart by the Milky Way's gravitational pull. In a few billion years, what was once an independent galaxy will be completely absorbed into the Milky Way, and its stars will become part of our galactic halo. Part 5. The Hidden Structures. Protogalactic fragments from our galaxy's infancy. Here's a discovery that really shows how much we're still learning about our own galaxy. Scientists recently found evidence of what might be the oldest building blocks of the Milky Way, ancient stellar structures that may have existed before the Milky Way itself fully formed. Shiva and Shakti, ancient ghosts of proto-galaxies. Using data from the Gaia Space Telescope, researchers in 2024 identified two massive stellar aggregations they named Shiva and Shakti. These aren't small structures. Each contains over 10 billion solar masses worth of stars. That's roughly equivalent to billions and billions of individual stars like our Sun. What makes these structures special is their age and origin. Evidence suggests that Shiva and Shakti may have formed more than 12 billion years ago. For context, the Milky Way itself is about 13.5 billion years old, and the universe is about 13.8 billion years old. So we're talking about structures that formed in the very early universe, just a few 100 million years after the Big Bang. The leading theory is that Shiva and Shakti might be remnants of proto-galaxies, small stellar systems that existed in the early universe and were eventually absorbed by the Milky Way. They could be fragments from even more ancient mergers than the famous Gaia-Enceladus collision we talked about earlier. What this tells us about galaxy formation. The discovery of Shiva and Shakti is significant because it reveals layer upon layer of complexity in the Milky Way's history. We now know that our galaxy didn't just go through one or two mergers in its early days. It went through many, many mergers and acquisitions, gradually building itself up from smaller and smaller components. This aligns with what we call hierarchical structure formation, the idea that small structures merge to form larger ones, which merge to form even larger ones, ultimately creating the massive galaxies we see today. The Milky Way is living proof of this fundamental principle in cosmology, but there's still so much we don't know. Scientists are still working to understand exactly when these proto-galactic fragments formed, how they interacted with the early Milky Way, and what role they played in establishing the structure of our galaxy today. Part 6. The AI Revolution in Astronomy. Simulating our galaxy with machine learning. One of the most remarkable developments in recent years isn't just a discovery itself, but rather a new tool that's allowing us to make discoveries. Artificial intelligence and machine learning are revolutionizing how we study the Milky Way. The challenge of simulating a galaxy. For years, astronomers have dreamed of creating a complete simulation of the Milky Way, a computer model that tracked every single star and could help us understand how our galaxy formed and evolved. But the challenge is enormous. The Milky Way contains over 100 billion stars, and simulating the gravitational interactions between all of them requires astronomical amounts of computing power. Traditional simulations had to use approximations. Instead of tracking each individual star, they would group stars together, essentially averaging the behavior of clusters of roughly 100 stars at a time. It's like if you wanted to simulate every grain of sand on a beach, but your computer couldn't handle it. So you treated each pile of sand as a single unit. It makes the calculation possible, but you lose detail. The problem with this approach is that important small-scale phenomena, like how individual stars orbit, how they interact with nearby stars, and how star formation happens in specific regions, get lost in the averaging process. You end up with models that are coarser and less accurate. AI to the rescue. In 2025, researchers at Riken in Japan, working with partners from universities in Tokyo and Barcelona, achieved something remarkable. They created the first Milky Way simulation that tracked over 100 billion individual stars, each one separately. They accomplished this by combining artificial intelligence with advanced numerical simulation techniques. Here's how it works. The AI learned how gas behaves in the galaxy, particularly after supernova explosions. Supernovae are incredibly important in galaxy evolution because they inject enormous amounts of energy into the surrounding gas, affecting star formation and galactic structure. By training a neural network to understand this complex behavior, researchers could eliminate one of the biggest computational bottlenecks. The result? A simulation that includes 100 times more individual stars than the most sophisticated earlier simulations, and it ran 100 times faster. Instead of taking months to simulate thousands of years of galactic evolution, the new simulation can do it in much less time. What this means for our understanding. This breakthrough has profound implications. With a detailed star-by-star simulation of our galaxy, astronomers can now test different theories against observational data with unprecedented precision. If we observe that certain stars are located in specific positions with specific velocities and compositions, we can simulate different scenarios to figure out what history would have produced those observations. This is particularly powerful when combined with data from Gaia and other telescopes. We can take what Gaia tells us about the current state of billions of stars and compare it to predictions from AI-enhanced simulations. The better the match between observation and simulation, the better our theories of galactic evolution. Moreover, this same AI simulation technology isn't just useful for astronomy. Researchers are already looking at how to apply these techniques to climate modelling and weather prediction, so the advancement benefits science across multiple disciplines. Part 7. The oldest light and earliest stars. Understanding our galaxy through its elderly residents. While researchers have been discovering new structures and phenomena, they've also been making progress on one of the most fundamental questions: when did the Milky Way actually start forming its first stars? The ancient star cluster. In recent years, astronomers have discovered and studied some of the oldest stars known to exist in our galaxy. Some of these are over 13 billion years old, nearly as old as the universe itself. These ancient stars are like cosmic fossils, carrying information about the conditions in the very early Milky Way. By studying the chemical composition of these old stars, scientists can learn about what the galaxy was like in its infancy. The earliest stars formed from gas that hadn't been enriched with heavy elements, what astronomers call metals, which include everything from carbon to iron to gold. As stars formed and eventually exploded as supernovae, they created heavier elements and scattered them into space. These enriched materials then went into the formation of the next generation of stars. So the older a star is, the fewer heavy elements it tends to have. By comparing the chemical compositions of different stellar populations, scientists can piece together a timeline of star formation in the Milky Way. When did the Milky Way form its first stars? Recent research suggests that the Milky Way may have begun forming its first stars within the first billion years after the Big Bang. That's incredibly early. The universe was young, conditions were chaotic, and yet somehow gravity managed to assemble the first stars that would become part of our galaxy. But here's where it gets complicated. Not all of these early stars were part of the Milky Way's main structure. Some of them formed in those proto-galaxies like Shiva and Shakti that we discussed earlier. When these proto-galaxies merged with the early Milky Way, they brought their ancient stars with them. So the Milky Way's history isn't just about one sustained process of star formation. It's more like a series of encounters and mergers, each bringing in stars of different ages and compositions. The oldest parts of our galaxy are these inherited populations, the stars that formed elsewhere and were later absorbed during mergers. Part 8. Understanding galactic structure. The disk, the halo, and everything between all these discoveries have helped us develop a much clearer picture of how the Milky Way is structured and how that structure came to be. The thick and thin disks 1. Important concept in galactic astronomy is that the Milky Way actually has 2 disks, not 1. There's a thick disk and a thin disk, and they have very different properties and histories. The thick disk contains older stars with higher velocities and more chaotic orbits. These are the stars that were part of the galaxy during the violent mergers of the early Milky Way. They were thrown up and out during these cosmic collisions, and they still haven't settled into perfectly circular, orderly orbits around the galactic centre. The thin disk is more orderly and contains younger stars, including our Sun. This disk formed after the major mergers had calmed down, roughly 6 to 8 billion years ago. By that time, the fresh gas in the Milky Way had settled into a flat plane, rotating around the galactic centre. It was in this thin disk that stars could form in a more orderly fashion, eventually leading to the beautiful spiral structure we see today. Understanding the difference between these disks has been crucial for understanding the Milky Way's history. It's like being able to see the layers of sedimentary rock in a canyon and understanding what geological events created each layer. The halo, a crown of ancient stars. The galactic halo is that spherical region of stars surrounding the disk. Many halo stars are incredibly old and have properties very different from disk stars. They move in more chaotic orbits, and many come from those ancient mergers. The halo is like a cosmic graveyard of past mergers. When you study the halo carefully, you can identify groups of stars that have similar compositions and motions, groups that likely came from the same progenitor galaxy. It's detective work on a cosmic scale. Scientists have identified at least 23 stellar streams in the galactic halo, elongated structures of stars that appear to have been torn from dwarf galaxies by the Milky Way's gravitational tidal forces. Each stream tells a story about a galaxy that got too close to the Milky Way and was literally ripped apart by gravity. Part 9. The future of galactic archaeology. What's coming next? We've covered what scientists have discovered, but what's coming next? What new revelations are on the horizon? Better telescopes? Better data. The Gaia mission continues to operate and collect data. Future data releases will provide even more precise measurements of even more stars. As this data becomes available, astronomers will be able to refine their understanding of galactic structure and history. Meanwhile, ground-based observatories are getting bigger and more sophisticated. Telescopes that will come online in the coming years will be able to measure things about distant stars that we currently can't even observe. This will give us a better view of the Milky Way's halo and the dwarf galaxies that surround us. Improved simulations. As AI and computational techniques continue to advance, we'll be able to run even more detailed simulations of the Milky Way. These simulations will help us understand not just what happened in the past, but also what might happen in the future. For instance, scientists can now simulate what will happen when the Milky Way eventually collides with the Andromeda Galaxy, a collision that's predicted to happen in about 4 to 5 billion years. Fundamental questions still unanswered. Despite all we've learned, fundamental questions remain. We still don't know what dark matter is. We still don't have complete clarity on the Milky Way's merger history. There are likely more ancient mergers waiting to be discovered. We're still learning about how galaxies form and evolve, but that's what makes this field so exciting. The more we learn, the more questions arise. Science is a never-ending journey of discovery, and the Milky Way is a fascinating destination. Part 10. Why this matters to us. Connecting cosmic history to human experience. You might be wondering, okay, this is all fascinating, but Why should I care about what happened to our galaxy billions of years ago? There are several reasons to appreciate these discoveries beyond pure intellectual curiosity. Understanding our place in the cosmos. First, these discoveries help us understand our place in the cosmos. We live on a planet orbiting a star in a galaxy that has an incredibly complex and dramatic history. The atoms in your body were created in stars and distributed through the galaxy by those ancient mergers and stellar events. In a very real sense, you're made of stardust that's been scattered across the Milky Way by billions of years of cosmic history. Understanding the Milky Way's history helps us understand ourselves. We're not just here by accident, we're the product of a specific cosmic history, and learning about that history deepens our connection to the universe. Testing fundamental physics. Second, these discoveries are testing the limits of our understanding of fundamental physics. How does gravity work on cosmic scales? How does dark matter behave? How do galaxies form and evolve? The Milky Way is our laboratory for exploring these questions. When scientists discover something that doesn't fit the existing theories, like too many satellite galaxies or a mysterious gamma-ray glow, it's an opportunity to refine and improve our theories. Sometimes, these refinements lead to entirely new understandings of physics. Technology development. Third, the technology developed for these astronomical discoveries often has practical applications. The sensors developed for telescopes end up in medical imaging devices. The computational techniques developed for galaxy simulations help with climate modeling. The artificial intelligence developed to analyze cosmic data helps with medical diagnosis and other applications. Inspiration and perspective. Finally, these discoveries inspire us and provide perspective. When you learn that your galaxy has collided with other galaxies, that your local neighborhood of space is part of a vast cosmic structure spanning billions of years, it can shift your perspective on what matters. It reminds us that we're part of something much larger than ourselves, and it can inspire curiosity about the universe. Part 11. The remarkable progress of astronomy. From telescopes to artificial intelligence. It's worth pausing for a moment to appreciate just how remarkable the progress in astronomy has been over the past few decades. When Galileo first pointed a telescope at the sky in 1610, he could barely distinguish individual stars. He could see that the Milky Way was made of stars rather than some sort of cloudy material, and that was revolutionary. But he had no idea how many stars there were, how far away they were, or anything about the overall structure of our galaxy. For the next 300 years, progress was slow but steady. Astronomers gradually realized that the Milky Way was an enormous disk of stars and that we were embedded within it. Then in the 1920s, a crucial debate took place. Some astronomers thought the Milky Way was the entire universe. Others thought there might be other island universes of stars beyond our own. The debate was resolved when Edwin Hubble used the 100-inch telescope on Mount Wilson to measure the distance to stars in the Andromeda Galaxy. They were too far away to be part of the Milky Way. We weren't the whole universe. There were other galaxies out there. But even with this knowledge, astronomers faced an enormous problem. The Milky Way was too vast and too crowded for them to map in detail. There were billions of stars, and measuring the distance and motion of even a few thousand was incredibly laborious. It required decades of careful work. The digital revolution. The real breakthrough came with the digital revolution and space telescopes. Starting in the 1990s, computer technology became powerful enough to process huge amounts of astronomical data. The Hipparcos Space Telescope, launched in 1989, measured the precise positions and distances of about 100,000 stars. It was groundbreaking at the time, but then came Gaia. When Gaia launched in 2013, It took the capability to another level entirely. Within a few years, it had measured the positions, distances, and motions of over 1 billion stars. That's not just incremental progress. That's a complete transformation of what we can observe. Think about it this way. If Hippocos gave us the ability to see individual trees in a forest, Gaia gave us the ability to see the entire forest, every tree in it, and how each tree is moving. It fundamentally changed what we could learn about the Milky Way. The AI accelerant. And now, with artificial intelligence, we're at another threshold. Machine learning algorithms can identify patterns in billions of data points far faster and sometimes more effectively than humans can. They can classify stars, identify structures, and simulate complex physical phenomena that would have taken months to compute just a decade ago. It's remarkable when you think about it. In just over a century, we went from barely seeing individual stars to being able to catalogue and analyse billions of them, understand their motions, and reconstruct our galaxy's entire 13.5 billion year history. That's an unprecedented acceleration in human knowledge. Part 12. The Continuing Mysteries. What we still don't know. But here's the important reminder. Despite all this progress, we still have enormous gaps in our knowledge. The dark matter question. Let's return to dark matter for a moment. It makes up about 85% of all the matter in the universe, yet we don't know what it is. Scientists have proposed many candidates, weakly interacting massive particles, axions, primordial black holes, and others, but so far none have been definitively detected. Every observation of the Milky Way provides clues about how dark matter behaves. The way galaxies rotate, the way they move, the distribution of structures, all of these depend on dark matter. By studying our galaxy in unprecedented detail, astronomers hope to eventually narrow down what dark matter is. The galaxy formation problem. We've talked about how the Milky Way formed through mergers and collisions, but the details are still fuzzy. Why did certain mergers happen when they did? How much gas was involved? How did star formation respond to these events? We're getting better at answering these questions, but we're not there yet. Moreover, there are theoretical puzzles. For instance, simulations suggest that galaxies should have spent more time in certain phases of their evolution than observations show they did. Somehow, galaxy evolution happened faster in the real universe than our models predict. Understanding why is an open question. The nature of the galactic waves. We discussed the mysterious waves in the Milky Way's disk. Scientists have a leading hypothesis about what causes them, but they haven't proven it definitively. There could be other mechanisms at play. Understanding these waves fully might reveal new physics about how galactic structures respond to gravitational perturbations. The fate of satellite galaxies. We have about 500 satellite galaxies, some actively forming stars and others not. Why this variation? How will these satellites evolve in the future? Will they all eventually be absorbed into the Milky Way, or will some escape? These are open questions that future observations will help answer. Part 13. The Ethical Dimensions of Astronomical Discovery. Why we pursue knowledge. Before we wrap up, it's worth thinking about why we do this. Why spend billions of dollars on telescopes and billions of computer cycles on simulations to understand a galaxy that, in one sense, has nothing to do with our daily lives? The pursuit of understanding. There's something fundamentally human about curiosity. We want to understand where we come from and how the world works. This impulse to understand is part of what makes us human. It doesn't have to serve an immediate practical purpose to be valuable. The pursuit of knowledge for its own sake has dignity and worth. Long-term practical benefits. That said, these pursuits do have practical benefits, even if they're not immediately obvious. The technology developed for astronomy finds applications elsewhere. The computational techniques benefit other fields. The fundamental physics we discover about gravity and the structure of matter helps us develop new technologies. But beyond technology, understanding the universe helps us understand ourselves. It provides perspective. When we realize that our galaxy has collided with others, that atoms in our bodies were created in ancient stars, that we're part of a vast, interconnected cosmic system, it can shift how we think about our problems and priorities. Responsibility and humility. As we learn more about the universe, we also develop a sense of responsibility and humility. The universe is vastly larger and more complex than we are. We are small, temporary participants in something immense and ancient. This realization can inspire both humility and wonder. At the same time, we have a responsibility to maintain high standards of accuracy and honesty in science. When scientists discover something that contradicts existing theories, the ethical response is to carefully examine the evidence, consider alternative explanations, and be honest about what we know and don't know. Part 14. The next decade. What to expect in galactic astronomy. So what should we expect over the next 10 years? What new discoveries might be on the horizon? New data from established telescopes. The Gaia mission is expected to continue operating through the late 2020s or beyond. Each new data release will be more complete and more precise than the last. By the end of the decade, we should have even more refined maps of the Milky Way's structure and a better understanding of its stellar populations. Other telescopes are also constantly gathering data. The infrared astronomy satellites can peer through dust clouds to see stars hidden from visible light. Radio telescopes can detect emissions from the interstellar gas. Together, all this data is providing an increasingly complete picture of our galaxy. Advanced simulations. As computational power increases and AI techniques improve, simulations will become even more detailed and accurate. We might eventually be able to run simulations that can predict not just what happened in the past, but what we should observe right now in specific parts of the galaxy. When observation matches prediction closely, it means our understanding is getting better. There's also the possibility that simulations will reveal phenomena that astronomers haven't specifically looked for yet. A simulation might show that under certain conditions, you'd expect to see a particular pattern of stars or a specific distribution of gas. Astronomers could then look for that pattern and potentially discover new structures or phenomena. Discovery of more ancient mergers. As we've developed better techniques for identifying stellar structures that came from different progenitor galaxies, we've found more and more of them. It's likely that over the next decade, we'll identify even older mergers and better understand the complex history of how our galaxy was assembled. There might be evidence of proto-galactic fragments, even older than Shiva and Shakti. There might be entire populations of stars that came from galaxies that merged with the Milky Way so long ago that we've almost completely forgotten about them. Uncovering these ancient mergers will help fill in the timeline of galactic formation. Insights into dark matter. While we probably won't have definitively identified what dark matter is by 2035, we should have much better constraints on its properties. We'll know better where it's concentrated, how it responds to gravitational disturbances, and perhaps have ruled out some hypothetical dark matter candidates. This information will be crucial for theoretical physicists working to solve one of the biggest mysteries in science. The Milky Way will have been an essential laboratory for this research. Understanding galactic dynamics. As we observe the galaxy in more detail and simulate it more accurately, we'll develop an ever deeper understanding of how galaxies work. How do disk galaxies maintain their spiral structure? What maintains the galactic bar at the center? How do gravitational waves propagate through a galaxy? These are sophisticated questions, but over the next decade, we should have much better answers. Part 15. How you can participate. Citizen science and public engagement. One of the wonderful things about modern astronomy is that you don't need to be a professional astronomer to participate. There are several ways to engage with this research as a citizen scientist. Galaxy Zoo and similar projects. A project called Galaxy Zoo invites members of the public to help classify galaxies visible in telescope surveys. Even though AI is getting better at this task, human eyes and intuition are still valuable. By spending a few minutes helping to classify galaxy images, you're contributing to real astronomical research. The data goes to professional astronomers who use it for their research. Similar projects exist for other types of astronomical data. You can help identify transient phenomena, analyze spectra, or assist with other tasks that benefit from human pattern recognition. Amateur astronomy. If you're interested in actually observing the night sky yourself, amateur astronomy is more accessible than ever. Telescopes have gotten better and cheaper. There are communities of amateur astronomers who collaborate, share observations, and sometimes make genuine contributions to science. While you probably won't discover the next galactic merger using a backyard telescope, you can still participate in various observation campaigns, tracking variable stars, observing asteroids, or simply understanding the night sky better. There's something special about looking up and seeing the photons that have travelled light years through space to reach your eyes. Learning and sharing. Perhaps the simplest way to participate is to educate yourself about these discoveries and share them with others. When you learn about the Milky Way's fascinating history, tell your friends and family about it. When you understand something about the universe that surprised or amazed you, share that sense of wonder. Science advances not just through the work of professional scientists, but through a culture that values curiosity and evidence. By engaging with this knowledge and spreading it, you're participating in that culture. Part 16. The philosophical implications. What the Milky Way teaches us. As we've explored the Milky Way's history, several philosophical questions emerge. The story of merger and becoming one. Philosophical theme is the idea of merger and becoming. The Milky Way wasn't always what it is today. It became what it is through a series of collisions, incorporations, and transformations. Each merger brought new material, new influences, new possibilities. In a sense, this mirrors how life itself evolves. Organisms don't remain static. Through mutation and selection, they change and adapt. Through symbiosis, they sometimes incorporate other organisms into themselves. Life, like galaxies, is not about eternal stasis, but about constant transformation. This might seem abstract, but there's something beautiful about recognizing that transformation is fundamental to how the universe works at many scales. Change is not a deviation from the natural order. Change is the natural order. The problem of emergence. Another philosophical question is about emergence, how complex structures arise from simpler components. The Milky Way emerged from the interaction of billions of stars and the mysterious scaffolding of dark matter. The structure we see today wasn't designed or planned. It emerged from the interactions of countless components following the laws of physics. This raises questions about how much can emerge from simple rules applied to many components. What other structures, patterns, and phenomena in the universe emerge this way? Understanding this might help us understand complexity in general, whether in galaxies, in ecosystems, in societies, or in minds. Time and perspective. The Milky Way's history also teaches us about time and perspective. 13.5 billion years is almost impossible for a human to comprehend. We live for maybe 80 or 90 years. Our recorded history goes back a few thousand years. Even human evolution spans millions of years, which feels like an incomprehensibly long time. But the Milky Way's history spans billions of years. Events that we might think of as momentous, a galaxy merger, for instance, might take tens of millions of years to play out. The largest structures in the universe operate on timescales so vast that they're almost beyond human intuition. This perspective can be humbling. It reminds us that we are small and temporary, but it can also be liberating. If our galaxy has survived billions of years and countless mergers, perhaps we can also survive challenges that seem overwhelming in our immediate moment. If the universe operates on scales so vast, perhaps our individual problems are both more trivial and less important than we sometimes think. Part 17. The interconnectedness of science. How galactic astronomy connects to other fields. One of the exciting aspects of modern astronomy is how it connects to other scientific disciplines. Physics and fundamental forces. Studying the Milky Way helps us test theories about gravity. Einstein's general relativity predicts how massive objects should interact gravitationally. When we observe the actual motions of stars in the galaxy and compare them to the predictions of general relativity, we're testing one of the most fundamental theories in physics. So far, the observations match the theory remarkably well, though there are some anomalies we still don't fully understand. Particle physics and dark matter. As we discussed, understanding dark matter is one of the biggest challenges in physics today. Particle physicists are building experiments to try to detect dark matter particles. Meanwhile, astronomers are studying dark matter's distribution and behavior in the Milky Way. These two approaches complement each other. If particle physicists discover what dark matter is, it will help astronomers understand what they're observing. If astronomers discover constraints on dark matter's properties, it will help guide particle physicists' search. Chemistry and nucleosynthesis. The abundances of different chemical elements in stars tell us about how those elements were created. In the early universe, the only elements that existed were hydrogen, helium, and trace amounts of lithium. All the heavier elements, carbon, oxygen, iron, gold, everything on the periodic table, were created in stars. By studying the chemical composition of stars of different ages throughout the Milky Way, we can trace the history of element creation. This connects directly to nuclear physics, chemistry, and even biology. The carbon in your body was created in a star, ejected into space, and eventually incorporated into the planet where you evolved. You are literally made of stardust, and the Milky Way is the furnace where that stardust was created. Artificial intelligence and data science. The computational techniques and AI methods developed for analysing astronomical data are finding applications across many fields. Machine learning algorithms trained on astronomical data can be adapted for medical imaging, climate modelling, and countless other applications. The feedback goes both directions. Methods developed in other fields often get adopted by astronomers. Philosophy and cosmology. Finally, there's the deep connection between astronomy and philosophy. Questions about the nature of the universe, the origin of complexity, our place in the cosmos, these have always been philosophical questions. But astronomy provides empirical data that constrain our philosophical thinking. Part 18. Misconceptions about galactic astronomy. Clearing up common misunderstandings. As we wrap up, let me address some common misconceptions about what we've discussed. Misconception 1. We know the entire Milky Way. One misconception is that we've completely mapped and understood our galaxy. In reality, we've made enormous progress, but there's still vast territory that's not well understood. Large regions of the Milky Way are obscured by dust, making them difficult to observe in visible light. The interior regions are crowded with stars, making individual objects hard to distinguish. And we've only recently begun to catalogue the satellite galaxies surrounding us. Moreover, new discoveries are being made constantly. If you asked an astronomer 10 years ago about waves in the galactic disk or structures like Shiva and Shakti, they wouldn't have had answers. These are recent discoveries. There are surely more surprises waiting to be found. Misconception 2. These discoveries won't affect me personally. Another misconception is that these discoveries are purely academic, with no relevance to everyday life. But consider this. The technology in your smartphone involves physics that was discovered through trying to understand the universe. The medical imaging techniques that detect disease were developed using principles from astronomy. The computational techniques used in artificial intelligence were refined through processing astronomical data. Moreover, these discoveries connect to fundamental human concerns. Understanding the universe helps us understand our place in it, which influences how we think about problems, set priorities, and relate to each other. Misconception 3. Science is settled. A third misconception is that science has figured everything out, or that it should have by now. In reality, science is a process, not a destination. For every question we answer, new questions emerge. The mysteries we've discussed, what is dark matter? How exactly did the Milky Way form? What causes the galactic waves? These are genuine unknowns that scientists are actively working to solve. This isn't a failure of science, it's the nature of science. The universe is complex, and it's always more complex than we initially think. That's what makes it fascinating. Misconception 4. Scientists always agree. A fourth misconception is that scientists always agree with each other, or that, if they don't, one side must be right and the other wrong. In reality, healthy disagreement is part of science. Different researchers have different interpretations of data. Different theoretical frameworks suggest different predictions. These disagreements drive research forward as scientists try to determine which interpretation is correct. The important thing is that disagreements are resolved through evidence and careful analysis, not through authority or consensus. An individual scientist can be right against the prevailing view, but they need to make a convincing case supported by data. Part 19. The human element. The scientists behind the discoveries. Before we conclude, it's worth acknowledging the human element behind these discoveries. Science is ultimately done by people. People with curiosity, persistence, creativity, and sometimes stubbornness. Individual brilliance and collective effort. Some discoveries in astronomy are made by individual geniuses, but most are the result of collective effort across many research groups, often internationally. A discovery might combine data from multiple telescopes, simulations run by one research group, observations collected by another, and analytical techniques developed by a third. This collective nature of modern science is important to recognize. No single person owns the discovery of galactic structure. Instead, it's an accumulation of contributions from many people with different expertise, all working toward understanding. The role of failure. It's also worth noting that science includes a lot of failure. Hypotheses that don't pan out, observations that are misinterpreted, models that don't match reality. But failures are crucial to progress. When something doesn't work as expected, it forces us to reconsider our assumptions. Some of the biggest breakthroughs have come from unexpected failures, diversity, and inclusion. Finally, it's important to recognize that for much of history, science has been done by a relatively narrow demographic. Women, people of color, and people from non-Western cultures have been systematically excluded or marginalized. Modern science benefits from efforts to make astronomy and other scientific fields more diverse and inclusive. Different perspectives and life experiences bring new ideas and ways of thinking. As we continue to explore and understand the Milky Way, we're also working to ensure that this exploration involves scientists from all backgrounds. That's not just a matter of social justice, though it's also about doing better science. Let's take a step back and recap what we've learned. We started with the discovery that the Milky Way wasn't always one galaxy. It was built through multiple mergers and collisions with other galaxies. Gaia Enceladus stands out as the most famous of these ancient mergers, but it wasn't the only one. Shiva, Shakti, and other proto-galactic fragments reveal that the Milky Way's history is even more complex than we thought. We then discovered that our galaxy is actively rippling with enormous waves that span tens of thousands of light years. These waves reshape the structure of the galaxy and may be connected to its ancient violent past. We explored the mysterious gamma-ray glow at the galactic center and discovered that it might be caused by dark matter particles colliding with each other. This reinforces how the Milky Way's chaotic history shaped not just visible matter, but also the distribution of dark matter. We found that the Milky Way has far more satellite galaxies than we expected, potentially over 500. These dwarf galaxies are being torn apart by the Milky Way's gravity and will eventually be absorbed, becoming part of our galactic halo. We discussed how artificial intelligence is revolutionizing astronomy, enabling simulations that were previously impossible, and helping us identify patterns in vast datasets. And we've explored the philosophical and practical implications of these discoveries. The bigger picture. What ties all of this together is a fundamental shift in how we understand galaxies. We no longer see galaxies as static, unchanging structures that have always looked the way they do now. Instead, we understand them as dynamic, evolving systems shaped by collisions, mergers, and complex gravitational interactions. The Milky Way is not an exception to this. It's a beautiful example of it. Our galaxy is a palimpsest, a manuscript that's been written over multiple times. Each merger left its mark. Each transformation added new layers. To understand what we see today, we need to understand what happened in the past. Why this matters? This understanding matters because it changes how we see ourselves. We're not living in a static, eternal galaxy. We're living in a galaxy with a history, shaped by ancient events and still actively evolving. The Sun formed about 4.6 billion years ago from the remnants of previous stars, orbits in a galaxy shaped by billions of years of cosmic collisions. Understanding this connects us to the deep history of the universe. It reminds us that we are part of something vast and ancient. It inspires wonder and curiosity, and it drives us to keep asking questions and seeking answers. The future? As we look forward, new discoveries will continue to reshape our understanding. Improved telescopes will reveal more details. Better simulations will test our theories. New techniques will help us see parts of the galaxy previously hidden from view. Some of the most exciting discoveries might be ones we haven't thought to look for yet. That's the nature of exploration. When you venture into unknown territory, you sometimes find things you never expected. But whatever the future holds, one thing is clear. The Milky Way has a remarkable story to tell, and we're only now beginning to read it. Next time you look up at the night sky and see the Milky Way stretched across the heavens, remember that you're looking at the product of billions of years of cosmic history. Those photons reaching your eyes have traveled through a galaxy shaped by collisions and mergers, animated by mysteries like dark matter and galactic waves, and populated by billions of stars at various stages of their lives. You're not just observing a collection of stars, you're observing a history, a process, a living and evolving cosmic system. And in a very real way, you're observing home. Thank you for joining me on this journey through the Milky Way's hidden past. We've travelled through billions of years of galactic history, from ancient mergers to recent discoveries. We've met some of the mysteries that still puzzle scientists: dark matter, galactic waves, and the properties of dwarf galaxies. As we continue to explore and understand our galaxy, remember that science is ultimately about curiosity. It's about asking questions and seeking answers. It's about looking at the universe with wonder and respect. The Milky Way's story is far from complete. There are chapters yet to be written, mysteries yet to be solved, and discoveries yet to be made. The universe is vast, complex, and beautiful, and the more we learn about it, the more we appreciate that complexity and beauty. Thank you for watching, and keep looking up.